This lesson deals with a direct reading or direct indicating magnetic compass and describes the principle of operation, the effects of acceleration and turning errors, and how to interpret the direct reading compass indications in a turn. A magnetic compass uses the horizontal component of the Earth's magnetic field to indicate the direction over the surface of the Earth of the magnetic poles, and the aircraft's heading is based on this magnetic datum. The direct reading magnetic compass enables the pilot to directly read the aircraft's heading from a pivoted magnetic compass assembly. The vertical card compass, or E-type compass as it is commonly known, is a type in general use. It is quite usual for the E-type compass to be the main magnetic reference source in a light aircraft and a standby compass in larger aircraft. The maximum permissible deviation on any heading is 10 degrees. The E-type compass consists of a circular compass card attached directly to the magnet assembly, which is suspended in liquid within a compass bowl. A vertical lubber line on a glass window in the compass casing enables the heading to be read off the compass card. Later in the lesson, we will try turning onto a heading using the E-type compass to see how it works in practice. In the meantime, we need to consider the three basic properties a direct reading compass must possess. They are horizontality, sensitivity, and a periodicity. Let's look at each one in turn. It is the horizontal or H component of the Earth's magnetic field, which enables the compass magnets to positively align themselves with the Earth's magnetic field in a north-south direction. The Earth's magnetic field will only be horizontal, however, along the inclination line, or magnetic equator. Even in mid-latitudes, lines of magnetic force in the Earth's magnetic field dip significantly below the horizontal. A freely suspended magnet assembly would follow the angle of dip, so to counteract this effect, the magnet assembly is pendulously suspended. A non-pendulously suspended magnet would take up the inclination of the local dip, like this. By suspending it from above, on a sharp pin sitting in a smooth, hard cup, we displace the centre of gravity from the centre. This produces a self-levelling mechanism. The centre of gravity will seek the lowest point. This means that the tilting effect caused by the vertical or Z component of the Earth's magnetic field is opposed by the weight of the magnet assembly, and the tilt or dip will be greatly reduced. Unfortunately, as we shall see later, this solution introduces new problems, called turning and acceleration errors, which we will discuss shortly. The sensitivity of a magnetic compass is its ability to accurately point to magnetic north. Two factors will affect this. The first is the strength of the Earth's magnetic field. The second factor is the pole strength of the compass needle or assembly. The weak magnetic field of the Earth cannot be altered. So to increase the sensitivity of the compass, multiple short magnets with a high degree of magnetism are incorporated into the magnet assembly. Sensitivity is further increased by reducing friction, and this is achieved in three ways. The first is to use an iridium-tipped pivot in a jeweled cup. The second is the lubricating effect on the pivot by the liquid which fills the compass bowl. And thirdly, the liquid in the compass bowl helps reduce the effective weight of the magnet assembly, as liquid is denser than air. A periodicity is a measure of how quickly the magnetic compass settles down to accurately point towards north again after being displaced. Any oscillations of the compass needle around magnetic north must be damped out or substantially reduced, and this is achieved in two ways. The first is the use again of multiple short magnets in the assembly. In this way, the mass of the magnet assembly is kept near the centre of the unit, which reduces the moment of inertia. The second way is the use of liquid in the compass bowl. This acts as a damping agent. However, when using liquid in this way, there are two other issues to consider. The first is that liquid may expand or contract as temperature changes, and this can be overcome by incorporating an expansion chamber. The second issue is that of liquid swirl, and this occurs as a result of the viscosity of the liquid. During a turn, the liquid in contact with the inside of the compass bowl tends to be dragged around with the bowl. Therefore, the liquid tends to swirl in the same direction as the aircraft's turn, and drag the magnetic assembly with it in the same direction. This results in the compass indicating an incorrect reading during a turn. Use the replay facility to become familiar with the effect of liquid swirl. Turning and straight line acceleration errors can be quite substantial in the direct reading compass. So we will devote the rest of the lesson to these errors and how we deal with them, starting with errors resulting from straight line or linear acceleration. So to begin, let's look at the effect of a straight line or linear acceleration on the compass reading, and then we will look at why the effect arises. Let's accelerate an aircraft on a heading of due west, or 270 degrees in the northern hemisphere. Watch the compass heading, and we can see that as the aircraft accelerates, the compass tells us we are turning to the right, even though the aircraft's true track has remained in a straight line. Now let's look at the reason why this error occurs. Linear acceleration errors occur in direct reading magnetic compasses because the magnet assembly is pendulously suspended. If the centre of gravity of the compass assembly is not directly beneath the pivot point, as we can see in the diagram here, a couple will be set up between the direction of acceleration and inertia acting through the centre of gravity, which results in a turning moment. As magnetic dip causes the pivot point and the centre of gravity to become misaligned, it follows that where a turning moment can be created by magnetic dip, a turning error will occur. Let's look again then, with the help of our diagrams, at an acceleration on a heading of due west, or 270 degrees in the northern hemisphere. Because of dip, we can see that the end of the magnet which is attracted to the nearest terrestrial magnetic pole, in this case the North Pole, hangs down below the horizontal. This means that the magnet's pivot point is no longer overhead the centre of gravity. Instead, we can see it is closer to the nearer pole. The acceleration acts on the pivot point. However, the reaction to the acceleration acts on the centre of gravity. This produces a turning moment or couple, which causes the compass needle to rotate, even though the aircraft is not turning. It is worth noting that where magnetic dip occurs, regardless of which hemisphere we are in, an acceleration always results in an apparent turn towards the nearest magnetic pole. In deceleration, the opposite rules apply, and deceleration always results in an apparent turn towards the magnetic equator whenever magnetic dip occurs. It follows also that except for a small amount of liquid swirl effect in turns, there will be no acceleration errors at the magnetic equator because there is no magnetic dip at the magnetic equator. There will be no acceleration errors on north or south headings either, as on these headings both the pivot point and the centre of gravity are in alignment with the aircraft's fore and aft axis. Let's look at turning errors now. Apart from the small error caused by liquid swirl, a turning error is an acceleration error, as any turn is effectively an acceleration in the direction of the turn. The basic theory is therefore the same as that for linear acceleration errors. Remember that acceleration errors occur where there is significant magnetic dip. Turning errors are maximum when turning through north or south. The error increases with magnetic latitude because magnetic dip increases. If liquid swirl is ignored, the errors will be zero when turning through east or west. Turning errors are usually more significant than linear acceleration errors for the following reasons. Turns are generally of greater magnitude, which results in a greater displacement of the magnet assembly. Turns occur more often and are likely to last longer than linear accelerations. Let's look at some actual examples of turning errors. Suppose we now consider what happens to the compass reading when an aircraft executes a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. To understand what happens, there are two things we have to bear in mind. The first thing to remember is that the example is in the northern hemisphere, and so the red end of the magnet will hang down below the horizontal because of magnetic dip. The pivot point of the magnet assembly will not therefore be over its centre of gravity. Instead, it will be nearer the red end of the magnet. During the turn, the magnet will be dragged to the left by the pivot point, while inertia will react through the centre of gravity. As these forces are not in line with each other, a couple is created which causes an anti-clockwise turning effect, moving the red end of the magnet to the left and the blue end of the magnet to the right, as we look at it here. The second thing we have to bear in mind, and this is fundamental to our understanding of turning errors, is that the compass rose card is orientated to enable the pilot to read the aircraft's heading directly from the compass card. This means that in order for the compass to read in the direction the pilot is facing, the compass card on the instrument will have to be orientated 180 degrees about the cardinal points of the compass. We can see this here, and it will help our understanding if this image is kept in mind. Remember that the compass card is fixed to the magnet, while the lubber line is fixed to the compass casing. So if the magnet swings anti-clockwise when viewed from overhead, the compass reading will increase, or overread. Conversely, if the magnet swings in a clockwise direction, the compass will decrease, or underread. Now let's return to looking at a left-hand turn from 045 degrees to 315 degrees through north in the northern hemisphere. Following the aircraft round the turn, we can see that although the aircraft has turned 90 degrees around the compass, during the same period of time, the magnet has rotated in the same direction by, say, only 70 degrees. Look closely, and we will see that only around 70 degrees have passed behind the lubber line and the compass overreads. In effect, the compass needs to catch up with the aircraft. So when the aircraft is on the desired heading of 315 degrees, the compass is indicating approximately 335 degrees. In order to turn the aircraft onto the desired heading of 315 degrees, therefore, the turn must be stopped when the compass reads 335 degrees or 20 degrees early. The compass will then catch up to read correctly. Think about it. Now let's look at what happens if we carry out a right-hand turn from 315 degrees to 045 degrees through north, again in the northern hemisphere. As before, because of magnetic dip, the red end of the magnet hangs down below the horizontal, and the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, there will be a couple causing a turning effect, moving the red end of the magnet to the right. Although the aircraft has turned 90 degrees around the compass, the magnet has been rotated in the same direction by a small amount, say 20 degrees. We have only seen 70 degrees pass behind the lubber line, and the compass underreads. In order to stop on the correct heading of 045 degrees, the turn must be stopped on 025 degrees or 20 degrees early. Let's suppose we turn an aircraft to the right from 135 degrees to 225 degrees through south in the northern hemisphere. Once again, because of magnetic dip, the red end of the magnet hangs down from the horizontal. And as before, the pivot point will be nearer the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the right by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created causes a turning effect, moving the red end of the magnet to the right. If the result of this is difficult to envisage, remember that we are now facing in a southerly direction in the northern hemisphere. Although the aircraft has turned 90 degrees around the compass, this time the magnet has been rotated in the opposite direction by a small amount, say 20 degrees. We see 110 degrees of heading change briefly, and the compass overreads. In order to stop on the correct heading, the turn must be stopped when the compass reads 245 degrees or 20 degrees late. By now, we should be able to work out on our own what happens when we turn from 225 degrees to 135 degrees in the northern hemisphere through south. Click on Continue when you have decided what compass heading you must stop the turn on. The answer is that we are turning left, and we should stop the turn when the compass reads approximately 115 degrees, or in other words, 20 degrees late. As before, because of magnetic dip, the red end of the magnet hangs down from the horizontal, and the pivot point will therefore be nearer to the red end of the magnet. The pivot point is no longer over the magnet assembly's centre of gravity. During the turn, the magnet will be dragged to the left by the pivot point. However, the inertia will react through the centre of gravity. As these forces are not in line, the couple created will cause the red end of the magnet to move to the left. As with the turn to the right, from 135 degrees to 225 degrees, we should stop the turn late. As a general guide to how soon or how late to stop a turn, it is worth noting that for a rate 1 turn, the turning error will be approximately 20 degrees. Rate 1 turns are commonly used in instrument flight, and in a rate 1 turn, it takes 2 minutes to turn through 360 degrees. For a rate half turn, allow a turning error of 10 degrees. And for a rate 2 turn, allow a turning error of 30 degrees. To conclude the lesson, this table summarises turning errors in the northern hemisphere. In the southern hemisphere, the errors are the exact opposite. The term sluggish, which appears in the right-hand column, means that the compass heading is lagging behind the aircraft heading. Liquid swirl will increase the turning error. Conversely, when the term lively is used, the compass heading is leading the aircraft around the turn. Liquid swirl in this case will reduce the turning error. The following rules apply. During a turn through the pole which is physically nearer the aircraft, the compass will be sluggish. It is therefore necessary to stop the turn early on the indications given by the direct reading compass. During a turn through a pole which is physically further from the aircraft, the compass will be lively. It is therefore necessary to stop the turn late on the indications given by the direct reading compass. At the magnetic equator, there is no dip. Therefore, the only turning error will be due to liquid swirl. Liquid swirl may account for a compass heading lag of around 5 degrees, or 5 degrees sluggish. Remember, it is the displacement of the magnets in a clockwise direction when viewed from above, which causes the compass to underread. A displacement in an anti-clockwise direction causes the compass to overread.